Hey guys, Ms. Gosling here. In this video, you are going to learn about magnetic flux and Faraday's law. By the end of this video, you will be able to define magnetic flux and magnetic flux linkage. You'll also be able to use them to solve problems. So let's go ahead and get started by introducing the concept of electromagnetic induction. So this video is going to go into a lot of the connection between electricity and magnetism, and electromagnetic induction is kind of the center of that. So what electromagnetic induction is, and electromagnetic induction is a potential difference, which you may have also seen, or which you've definitely seen written in other words. So for example, you've seen PD, we've seen EMF, we've seen voltage. This is, of course, the thing that causes electricity to move around a circuit. So a potential difference can be created in a wire due to a changing magnetic field. So what we're looking at is, so we can talk about a magnetic field changing, but I think what might be an easier explanation to start off with is thinking about a wire moving in a magnetic field. So say I have a magnetic field here, B. And we can even say this is between, the north and the south poles of a magnet. And say I take a wire of length L, and I move it into my magnetic field. Moving the wire into my magnetic field is going to generate a potential difference in the wire due to the changing amount of wire that is in the magnetic field. So in this case, the wire's relationship to that magnetic field, the amount of wire in the magnetic field, the speed at which it moves through that magnetic field, is going to create that potential difference versus the magnetic field itself changing. And we can actually calculate that potential difference created in the wire using the equation EMF is equal to the magnitude of the magnetic field times the speed of the wire times, of course, the length of the wire that is actually in the magnetic field. So that is the first way that we can generate a current due to a magnetic field. So again, instead of hooking our wire up to a battery, what we can do is we can stick it in a magnetic field, and that potential difference created is going to create a current. I do, however, want to caution you here. Remember that our currents are only going to arise in a closed circuit. So this example I gave you with a single length of wire isn't going to generate a current because we don't have a closed circuit. But if we were to look at, for example, a loop of wire being moved into the magnetic field, that is going to create a nice circuit for us, and we're going to generate a current due to that potential difference generated in the wire because of electromagnetic induction from its motion in the magnetic field. Now, I do want to go ahead and quickly mention that we can also add in the sine theta term, with theta being the angle between the wire and the magnetic field if the wire and magnetic field are not perpendicular. So that's another important thing to think about, is making sure, remember that your magnetic field needs to be perpendicular to your wire for that magnetic field to induce a potential difference and therefore a current in the wire. So if we are set at some kind of an angle to that magnetic field, then that angle theta, we're going to take the sine of that angle to figure out the proportion of our wire that is perpendicular to that magnetic field. To figure out the proportion of that magnetic field that we actually have to look at when we're figuring out our electromagnetic induction. So with that, I want to go ahead and introduce a new term, and that is magnetic flux. And magnetic flux, we are going to define as the component of magnetic field through a surface. And that magnetic flux is going to be proportional to the number of field lines. So the more field lines, the greater the magnetic flux. So say I have a magnetic field coming straight up from the bottom of the page, and I want to figure out the magnetic flux in, say, a rectangular area going out and into the page. So this is kind of going into that page here. What I can say is that the magnetic flux through this surface, this area that I've drawn, is equal to, and we're going to use this symbol here, a phi, to represent our magnetic flux. which we are going to measure in Webers. And I can say that that is equal to the magnitude of my magnetic field times the area of my chosen surface. And then finally, you see here we have this cosine theta term. And we're only going to use this if our area is not perpendicular to our magnetic field. So if our area is not perpendicular to a magnetic field, we only care about the part of our surface that is perpendicular to that field. So we'll take the cosine of the angle between magnetic field and our area. And again, only if my magnetic field is not perpendicular to my area. So there you have it, guys. This is our introduction to what magnetic flux is. Now we're going to talk about one last thing before we get on to the whole point of all of this. So magnetic flux linkage is the component of magnetic field passing through a coil of wire. So in this case, we have our magnetic field here. And through our magnetic field, we have a coil of wire like so. So our coil of wire is perpendicular to our magnetic field. In fact, perhaps I should draw it a little bit differently to show that. So we've got our wires kind of going behind our field and then in front of it. And we can, in fact, have multiple coils of wire that are all linked to one another like this, hence linkage. We've got multiple coils of wire in our field. So what we can say is that the magnetic flux linkage in the wire, so that kind of total flux throughout the wire, is equal to the number of coils times the magnetic flux through a single coil. So B is going to be, of course, magnetic field, and A is going to be the area of our wire. Okay, so now let's go ahead and get to the point of this. And that is a beautiful law called Faraday's Law. And I personally think Faraday's Law is incredibly profound because Faraday's Law connects electricity and magnetism in a really beautiful way. So what we can say is that a changing magnetic flux, so the change in our flux over time, is equal to our EMF. And that's for a single coil of wire. If we add multiple coils of wire, then we can say that our EMF is equal to so this is of course our induced EMF, and that's going to be equal to the number of coils of wire times the magnetic flux, which is of course B times A, divided by the change in time. So when we have a magnetic flux changing over time through a coil of wire, that is going to induce an EMF in our wire. And of course, when we induce an EMF, we induce a current. Now, the last thing that I would like for us to talk about is that negative sign. So this negative sign actually comes from something called Lenz's law. And Lenz's law states that the current generated due to a changing magnetic flux will change, or perhaps more accurately, will flow in such a direction that it opposes that change in flux. So essentially what Lenz's law is saying is that just like how masses don't like to change their motion, currents don't like to change themselves. So let's go ahead and look at what that actually looks like. So say I have a magnetic flux B, which is generating a current in this yellow loop of wire. Lenz's law is going to help us figure out the direction that current is going to flow. Because we know, of course, that usually a current can flow either in this direction or that direction around the wire. We can either go clockwise, as in the first picture, or counterclockwise, as in the second. Lenz's law will help us figure out whether picture A or picture B is correct, whether we flow clockwise or counterclockwise. And what I want to do is I want to take a look at the magnetic field around a current, because I know that a current generates a magnetic field of its own. So using my right-hand rule on my clockwise current, let me see if I can draw a hand. I'm not so good at drawing hands, y'all. We're going to do our best. So I have my thumb lined up in the direction of my current and my fingers wrapping around. And I can see that my fingers at the point that the current, inside my loop, so at the same point that we're looking at within our surface, my current generated by, or the magnetic field generated by my current is going to point directly down. Like so. And so it's going to oppose the magnetic field that generated the current. Now let's look at option B. So again, I'm going to line up my thumb so that it's of my right hand, so that it's in the direction of my current. And I'm going to wrap my fingers around. And I can see that within my wire, so within the surface that I'm interested in, the magnetic field generated by my current is going to go up. Or it's going to add to the magnetic field that created it. And when that magnetic field adds, what's going to happen is the current is going to continue to increase. And the magnetic field would increase, the current would increase, and so on and so on and so on until infinity. And of course, we know that this is not possible because of the law of conservation of energy. So Lenz's law is essentially saying energy is conserved in circuits as well as in other situations. And the way that energy is conserved when we're looking at magnetic induction, at electromagnetic induction, is by the current generated by that electromagnetic induction creating a magnetic field that opposes the magnetic field that created it. So with all of that, let's go ahead and move into our first example. The graph here shows a variation of magnetic flux with time through a coil of 500 turns. What we want to do is calculate the magnitude of the EMF induced in the coil. So we know that EMF is equal to negative N d phi by dt. And we can figure out the change in phi over time, the change in magnetic flux over time, by finding the slope of my graph. I also know, of course, that N is the number of coils, which is 500. So let's go ahead and do that. So EMF is equal to negative 500 times the slope of my graph. And I'm going to go ahead and pick 2 points on my graph that seem nice. And I'm going to actually pick my first and my last points. So we are going to do our rise over our run. So 2.5 minus 0 over 5 minus 0. Or EMF is equal to negative 500 times 2.5 over 5. Or my EMF is equal to negative 250 volts. And there we go. So now let's take a look at a second example. A small cylindrical magnet and an aluminum cylinder, which is non-magnetic, of similar shape and mass are dropped from rest down a vertical copper tube of length 1.5 meters. First, we want to show that the aluminum cylinder will take about 0.5 seconds to reach the bottom of the tube. And this is actually a really fun problem. So we have a cylinder falling down a tube, no friction, no magnetism. This cylinder is actually going to be in free fall. And so we're going to go back to last year, and we're going to be solving this problem using a Suvat table. So we know that because my aluminum cylinder is in free fall, my initial velocity is 0, and my acceleration is negative 9.8. I also know that it falls negative 1.5 meters. Or it falls 1.5 meters, so its displacement is going to be negative 1.5. And I'm trying to show that it takes about 0.5 seconds to reach the bottom of the tube, so my time is going to be my unknown. So, knowing that V is my extraneous variable, I will be using the equation S equals ut plus 1/2 at squared to solve this problem. Guys, I also just want to note, if this does not ring a bell, if you feel like you can't do this on your own, I want you to go back and I want you to review last year what we learned about kinematics, because this is a really fundamental thing to be able to do. Anywho, moving forward, let's plug in some numbers. We know that our displacement is negative 1.5 and our initial velocity is 0. So 0 times t plus 1/2 times negative 9.8 t squared. So my first term will disappear since 0 times anything is 0. That's going to give me negative 1.5 equals negative 4.9 t squared. Or, solving through all of this, t is equal to 0.55 seconds. And that is going to be my answer to part A. Part B is asking me to explain, so part B, I see that the magnet takes 5 seconds to reach the bottom of the tube versus the aluminum cylinder, which took a longer time. And I'm getting asked to explain why. And my explanation here, guys, is that the cylindrical magnet falling through the tube is going to generate an EMF in the walls of the tube. So falling magnet has a changing magnetic flux, which is going to generate current / EMF in tube. That current is going to oppose the motion that caused it. So since the magnet is falling down, we know the current will be directed, or we know that the EMF, or that the current is going to generate a magnetic field that goes up. So just like the changing magnetic field of the magnet is going down, the changing magnetic field generated by the current in the copper tube is going to be directed up. So current in tube generates upward magnetic field due to Lenz's law. And so that magnetic field is going to exert a force on my magnet that is going to be pointed upwards. So my magnet is going to have gravity pulling it up, or pulling it down, just like the aluminum cylinder, but it's also going to have a magnetic force pulling it up. And because of that, it is not in free fall and will therefore take a longer time to fall. So there you have it, guys. That is our video. Let's talk takeaways now. First of all, a changing magnetic fluxes causes EMFs and thus currents to arise. And that is something that we call electromagnetic induction. Second, Faraday's law helps us determine the magnitude and direction of the currents that arise due to electromagnetic induction. And we particularly are going to look at Lenz's law when we talk direction. So there you have it, folks. You have been introduced to electromagnetic induction, Lenz's law, and Faraday's law. Now it is your turn to use all this information to solve a couple of problems. Best of luck and happy solving.